Hello everybody. Let's solve some Hooke's Law problems. So everyone did well in the lab. It was a pretty easy lab. Now, applying it, pretty straightforward too. We've got a lot of forces that have this direct relationship. Friction is directly related to normal force and the coefficient of friction. Spring force directly related to stretch of the spring and the spring constant, right? We've got Hooke's Law that says the force that a spring exerts is equal to, and if we do it vectorially, there's a negative, the opposite of k times x. And that opposite just has to do with the direction of the x, the stretch or compression, and the direction of the force that the spring exerts. Now in this case, we've got a horse laying on a platform, I guess at the vet's office or something. Though if you have a horse, that's probably pretty difficult. And a spring that is compressing. Although this is probably how they weigh horses, but not up on a big platform, probably one that's on the ground. So we know that the horse is laying on the platform, that the spring is compressed. That's our x. Our x is 0.21 meters, as it says right there. The constant, that's the lowercase k. We want to find the weight of the horse. Well, since he's supported on that platform, if we draw a force diagram, a free body diagram, if that's our horse, it's being held up technically by the platform, but the platform is being held up by the spring. So we're going to say that that's the spring force. And it's being pulled down by the force of gravity. And there is no acceleration. So that tells us that the sum of the forces has to equal 0, since the sum of the forces typically equals ma, but we know a is 0, so therefore that's going to be 0. Now those forces, we'll do ups minus downs. That's the spring force minus gravity, which I wrote in as mg, because that's how you find gravity. But I don't need, now I'm going to stop there. I want to find the weight of the horse, which is the force of gravity. So I don't need mg in this one. Mg is if you want to find mass or your given mass. F sub g is the force of gravity, is the weight of the horse. So I can leave this as F sub g. That's going to be 0. So we know in this case, the spring force is going to equal the gravitational force's magnitude, since there's no acceleration. Now this is Newton's second law. If there was an acceleration, these forces wouldn't be balanced, but then the horse wouldn't be sitting there. So we know this is true, that the spring force has got to equal the weight of the horse. Well, the spring force is found here. Now this negative, that is only used when you use this equation alone and you put in directions of the compression and force. I recommend you just use your head. You think about it to determine the direction of the spring and the direction of the compression. So the x was down, so that means the spring force is up. That's all that negative means, but I can figure that out in my head. So I don't need to put any kind of negative in here. I just need kx. So this is going to give me that kx is going to equal Fg, the force of gravity. So k is given to me right there. I got 10,850 times x, and x is 0.21, 0.21 meters. That's going to equal, running out of space, there. So that's going to multiply out, pop that in my calculator. Right, and we've got 2,278.79 because it was 0.5. It was 2,278.5, but I think we got to put all whole numbers in this answer. So there's my answer: 2,279 newtons. That's a pretty light horse. So, pony. Now the next one. We're doing another problem like this that you have in today's assignments. All right, we've got a graph of spring force and a question about that graph. So the graph of the force applied to a spring and the corresponding stretch of the spring is shown over here. How far in meters would this spring stretch if 0.75 kilograms mass is hung from it? All right. Well, we can see this graph is in millimeters, first of all. Got to be careful of our units. Millimeters for the stretch, newtons. Now the force that a spring exerts, its magnitude, if I just do absolute value, is equal to the absolute value of K times X. That's the size. The size of the spring force is equal to K times X. Well, K, that is the slope of the Fx graph for a spring. That's the slope of this graph. So if I want to find how far, that means I want to find X. X equals what? I've got to find the X here. I need the K. The K is going to come from the slope of this graph. So it intercepts 0, 0. So I can go up till the graph is hard to read. Let's try to find something that's intersects pretty well. All right, after looking at this carefully, it looks to me like right here I've got, let me zoom out a little bit. Boom. Bang, bang, bang. I've got here 5 newtons. That's a 5. And then down here, it's got 15, 16, 17, 18 millimeters. So my slope is the change in the y-axis over the change in the x, which is 5 minus 0, 5 to 0, divided by 18 minus 0, 18 millimeters minus 0. So it's going to give me 5 over 18, but that's newtons per millimeter. Right, that's newtons over millimeters. I need newtons per meter, I think. Yeah, because I want to find my answer in meters. So I want this slope in newtons per meter. So I'm going to take this and do a conversion. So I know that 1 millimeter, no, how about 1,000? 1,000 millimeters is 1 meter. And now that's millimeters on top. The millimeters cancel. Got meters left. So 5 over 18. 5 times 1,000 divided by 18. 277.77. So my slope equals 277.78 newtons per meter. So that's what my K is. K equals that. And now I can do the math to find X. So to find X, so rearranging this equation up here, I get that the stretch is equal to the spring force over K. Well, what's the spring force? It tells me mass. Well, when we hang a mass from a spring, draw it right here, right? If we have a spring right here and a mass hanging on it, well, this has gravity pulling it down and the spring holding it up. It's not moving, the acceleration 0, so as we've shown before, if it's not moving, then that spring up minus the gravity down is going to equal 0, so that spring is going to equal the gravity. So this force of the spring here I know is equal to the gravitational force on it, so I can plug that in up there. Now I'm going to move that down and stretch out my picture here. So we've got that X is force of the spring over K. But we also know that the force of the spring in this case is equal to the force of gravity because it's hanging in equilibrium. It's not always true, but it is now. So that stretch is going to be the force of gravity over K. And force of gravity is m times g, but that m has to be in kilograms. So let's move over to here. So our X is going to be equal to m, which is 0.75 kilograms, times g, which is 9.8 meters per second squared, divided by K, which I got to be 277.78 newtons per meter. So kilograms times meters per second squared, that's a newton. The meters go on top. I'm all good. So I plug that all in my calculator. I got 0.75 times 9.8 divided by 277.78. And that's what we get, 0.02645. And that's meters, right? 0.02646 meters. That's how you do that. I'll have to double check that problem and maybe make this not in meters, make it in millimeters. Okay, be careful of units on that. All right, here's another one where we've got a spring pictured, has an unstretched length of 6.8 centimeters. That's this, L1. That's my L1. A mass of 200 grams, that's that, is hung and gently lowered till in equilibrium. Its new length is 9.5, that's this. Centimeters, L2. What's the spring constant? Well, force on a spring is equal to, if we're not worried about direction, K times X. Okay, not worried about direction right here. Cool. So we have a weight hanging on this, a mass hanging on it. So once again, if we look at the forces on that mass, there would be the force of the spring up, there would be the force of gravity down, and since it's not accelerating, those have to add to 0. That spring minus the gravity, because it's down, will equal ma, but that's going to equal 0. So the spring is going to equal the gravitational force. And again, that's only because it's in equilibrium, because it's balanced, it's not accelerating, it's just hanging there. Well, we know that kx is going to equal mg, but we got to make sure all our units are correct. Right? We want the spring constant in newtons per meter. So we're going to have to change everything to newtons and meters. Well, x, what's x equal? X is going to be L2 minus L1, because this is the x right here. That's the stretch that you want. And in my case, that is 9.5 minus 6.8, which is what? 2.7? 2.7, if that makes sense. 2.7 centimeters. But we want to put things in meters. So that's going to be, divide that by 100. 0.027 meters. That's my x. Now mg, I need that to be m in kilograms. So mg, I got 200 grams here. I got to change that to kilograms. 200 grams times 1 kilogram per 1,000 grams. It's going to give me 0.2 kilograms. Whoop, can't see that. All right, sorry about that. I went off the paper. So this mg, m is 200 grams. Well, that's going to equal 0.2 kilograms because 1 kilogram is 1,000 grams. And you would do that conversion. So we now can figure all this out. We can find x, I mean k, solve for k here. K is going to be mg over x. So I've got 0.2 kilograms times 9.8 for g divided by 0.027 meters for x. Plug those all in. I get 75.59, 79.6. So K for me is going to equal 72.6 newtons per meter. That's how you do that. So be careful here. You got to change these lengths given to meters. You got to find the stretch. That's what's important. You got to find the weight because gravity is what's causing the spring to stretch, and the gravitational force is equivalent to the spring force when it's hanging there in equilibrium. And then we got to plug that in to here. We know that kx has got to equal mg because fs, which is the spring, is kx, and fg, which is the weight, is m times g. Plug it all in, figure it out. Hope that helps.